Okay, hello everybody. We are right on time. So today, I welcome everybody to our 113th Nice International Talk. Today, we're going to talk about is chain of thought reasoning of LMs a marriage or data distribution lens? And we will have Chengshuai, our speaker. Chengshuai is currently a second-year Ph.D. student at Arizona State University, advised by Professor Huan Liu. His research spanning across data mining, AI for science, repetition learning, and large language models, and he received several Best Student Paper Awards and Best Demo Awards. And I am today's host, Haolun. I'm a final year PhD at Mila McGill. So without further ado, let's welcome Chengshuai for presenting today's talk. Chengshuai, please share your screen. You can start anytime you are ready.
Yeah, of course. Thank you, Haolun, for your kind introduction. So I'm Chengshuai from the Data Mining and Machine Learning Lab at ASU. Today, I'm very glad and honored to have this kind of opportunity to give a talk at our NICE community. And today's talk, the topic is chain of thought reasoning of LLMs, Mirage, a data distribution lens. This actually is a paper that we put it on archive around October this year, and after we put it on archive, we actually receive a lot of feedback and suggestions regarding our work. So today we will discuss it a little bit. Um, Recent years have witnessed large models' dominant role in various domains through velocity prompting technique. Among them, I believe chain-of-thought prompting has shown to be very effective for eliciting structured reasoning from LLMs by simply appending a clause, say, let's think step by step. The large model are able to break down the question and output the intermediate process before arriving the final answers, which leave an impression that the large model are involving in the thinking process or the reasoning process, just like human. But if we consider a closer examination, it actually reveals inconsistency that may challenge this optimistic point of view. Let's say, consider this kind of question. On which day of the year was the US established in a leap year or a normal year? Let's think step by step. When we use this question to prompt Google's large model Gemini, it output the results like here is a step-by-step breakdown. And following it break down the question, the first step is actually identify the year US was established. Then the model try to figure out the rule for leap year and the normal year. And the third step is the large model apply this rule to the year identified and figure out it is a leap year. But when we look at it, the intermediate process are actually very perfect, very correct. And but when it comes to the final results, we find that actually the final results is incorrect. Such kind of inconsistency may suggest there's a distinction between human reasoning and large model thinking. So uh, most recently, I remember when GPT-5 was released, a lot of users, probably most of you, may find that its reasoning even fail on a very simple numerical computation task, right? So this could be another phenomenon. And moreover, I think a growing body of research suggests that reasoning of a large model may be more superficial than it appears. For example, Dr. Zhao's work witnessed the failure of reasoning of large model in planning and scheduling tasks. If you look at the figure here, when we increase the optimal planning length, the performance that is sacrificing of large model reasoning is also decreased. It's eventually it will vanish after the length equals 14th, right? And this kind of experiment conduct across different models from the GPT-4 to Llama to O1 is kind of a dominant perspective. And also, the similar results has also found in Apple's work, the illusion of thinking. In that work, they try to benchmark different kinds of puzzle tasks, like Tower of Hanoi, checker jumping, block world, and river crossing. This kind of puzzle task. They found that actually when we increase the complexity of this puzzle task, the large model's performance, the O1's performance actually drops a lot. And another branch of the work is referred to mathematical reasoning, like Professor Doan Song's work demonstrates that large models are struggling with complex mathematical problem. Here, they benchmark different kinds of mathematical reasoning problem from the numerical computation to linear algebra to like prime factorization problem. So so collectively, I would say that scientific research build upon the foundation laid by previous giant. But each of these pioneer work represent an uh, empirical contribution to what we term the mirage of large model reasoning. But sometimes, like the Plato's allegory of the cave, the shadow we preserved may be partial, and the empirical representation of a deeper reality. It actually motivates us to research further and explore the nature of chain of reasoning. So in this work, we propose a perspective, specifically a theory that is data distribution lens to study and understand the chain of reasoning. And for the data distribution lens, it actually contains of two sentences. Its chain of reasoning reflects structured inductive bias learned from in distribution data, allows the model to conditionally generate reasoning paths that approximate those seen during training. Thus, its effectiveness is fundamentally bounded by the degree of distributional discrepancy between the training data and the testing query, which means if you are lucky enough, your test case is falling into the training data, probably the larger model will give you the correct answer. Otherwise, it may not give you the correct answer, right? So by looking through this kind of a data distribution lens, we review that the underlying this kind of empirical mirage is this data distribution lens. That is this theoretical foundations. The framework demonstrated that the failure or the success of chain sort reasoning is not coincident, but be predictable. So for this kind of theoretical foundation, we first look at some mathematical intuition behind the data distribution lens. And at first, we try to define what is distribution discrepancy. We given the training distribution D-train and the test distribution D-test. The distribution discrepancy is defined as the delta D-train and D-test, where the H here is a divergence metric. It can measure the KL divergence or other distance that quantify the statistic distance between the training distribution and the testing distribution. Then later we try to figure out the boundary for the chance of generalization. So let F denote a model trained on D train with expected training risk R train. So R train here, we actually can estimate it by the cross entropy loss on the next token prediction of the training data. For the testing distribution d-test, the expected test risk R test is bounded by the following formula. We can see that the first term is actually R train. It's a risk of expected training risk plus the plus delta D train and D test. That is distributional discrepancy between the training data and the testing case. And add another content which is related to the number of training data. This kind of theorem carries some insight. For example, if you look at the first term R train, expect training risk, you will find that is actually related to models capacity or models architecture. But models capacity is also related to models architecture or models parameter size. Um, which means if you use a very, how to say, state of the art model or very advanced model, so the first term could be very low. The value of the first term is very low. And but even if in this case, so the R test is still bounded by the second term. That is the distribution discrepancy between the training data and the testing case. So that is we call it the fundamentally bounded. So eventually it will be our the data distribution lens. So after we know what is kind of a data distribution lens, we try to examine it, the scenario in the real world. Guided by this lens, we examine it, the chain of thought reasoning process and identify the three critical dimensions along which distributional shift can occur. Um, Specifically, it contains three different dimensions. The first dimension is task. It tries to examine the extent to which chunks of the reasoning of LLMs transfer across different reasoning tasks. For example, if we train large model on a specific like set of reasoning, can be generalized to novel problem which involves just a combination of existing reasoning, or even in a more extreme case, if we train large model in one domain, let's say mathematics domain, can it be generalized to another domain like healthcare domain, this kind of thing. And for the second factor, that is length. There's a lot of work also study the lens. It mainly talk about investigate the robustness of chain reasoning to reasoning chain of various lens. For example, if we the training data contains two-step reasoning, can large model trained on it be transferred to task which requires three-step reasoning or one-step reasoning? How it will perform? And the third point is actually the format. Format actually try to like explore how sensitive chain-of-thought reasoning is to variance in prompt formulation and structures. It actually refers to a real-world scenario which users can never design a golden prompt when prompt the large model because the golden prompt only resist in the training data. So in this way, when a user try to prompt a large model, they can only create a noised prompt, right? So how large model will respond in this kind of noise prompt. So so guided by this lens, we developed three different perspectives. So how can we empirically validate it? There could be several ways. But most of this work mainly evaluate on the shelf of a large model, like just evaluate GPT-5 or Gemini 3 without the training process. This kind of approach seems to be very appealing, but but uh, but it also may present several challenges. I would say the first challenge is opacity problem. That is, say, the company may release a weight of a large model nowadays, but they didn't release training data, right? So if we directly use this state of art open source model, but without acquiring their training data, that would be make it very difficult to us directly evaluate our data distribution length because we cannot determine it or measure the distribution discrepancy between the training data and the testing case, right? And another challenge is refers to the complexity because this company try to make the best of all the data available online to train their large model, which introduce confounders and make it very hard for us to isolate the factors we just mentioned of distributional shift and scientifically and rigorously investigate them, right? And so to use so So these two factor, which is the opacity and the complexity of their training data, would prevent us to draw any generalizable conclusions. To use an analogy, that is, one cannot conclude that a feather and a air ball fall at the same rate by testing them in the normal air rather than in a vacuum, because the complicated surroundings conditions, that is air resistance, would obscure the true law of gravity, right? So in this sense, we really need a clean and controllable environment to eliminate the contamination problem we just mentioned and isolate these spurious factors and probe chain sort of reasoning and investigate its true nature. So in our work, we propose a framework that called data alchemy framework, which is a very controllable, fully controllable and isolated framework, which allows us to train large model from scratch to avoid, we just mentioned, the data contamination problem. It also, because it is fully controlled, it also allows us to manipulate the training data distribution testing case. Also, the large model almost everything and systematically probe large model produce produce the chain sort of reasoning under different conditions and validate our theory. In this way, we can really isolate the different factors from the complicated environment and get a very solid and scientific result. So specifically, data alchemy environment encompose various abstract combination of element and transformations, representing a macrocosm of diverse NLP downstream tasks in the real world. So here, let's first recall how NLP tasks look like in the real world. So, large model, we use a large model in our daily life, like use it as annotator or use it as a judge. If we recall the scenario we used, we could use large model to explain some paper or classify some passage or judge or use it as a judge to just two responses like this. But if we summarize the before mentioned form, we can abstract them into an abstract form that is place perform such kind of action based on the test, right? Here the performed action could be its plan, classify and judge, and the test or the context here could be the operation or the action it operates on, could be the paper, the sentences, the response. So in our work, we try to um, use transformation to represent this kind of abstract collection of performed actions, and we use the element to represent a very abstract collection of the test. In this way, we actually distill the task in the real world to the combination of these various transformation and elements. So in this way, we try to cover all kinds of NLP tasks in real world. Specifically, the data alchemy framework is actually composed of several key component. The first component is the basic atoms. It's actually just alphabet letters from A to Z, totally 26. It's actually represent the token in the real world. Based on these basic atoms, we can further develop the element. For example, Apple, APPLE. This kind of element is consist of atom APPLE. These five different atoms. Here the length means here each element has one unique length, which means the number of these atoms for the element, it actually refers to can represent the test or passage in the real world. Based on the element, we can further develop the transformations. Uh, transformations here in our paper, we initialize two different transformations. One is root transformations. Root transformation has one parameter. Here we just for simplicity, we just use root 13 transformation. That is we mold the atom within the atom in alpha beta order for 13 position. Let's say if we input an apple, APPLE after the ROT root transformation, it will become an NCCYR, right? Because A plus 13 will become N. For the second transformation, we use a cyclic shift transformation. It just try to mold the atom within the element ahead or before, ahead or after some positions. So by initialize two different transformations, we actually wanted to represent the performed actions in real world. And by combining different kinds of element and transformation, we try to cover the different task in NLP task in the real world. So by doing this, we actually have some beneficials. That is, we can naturally acquire chunks of reasoning style by applying conversation of transformation and decompose the intermediate process. If we consider a conversation of transformation, fx here is a conversation of some basic transformation. Some let's say from f1, f2 to fk, right? Then we apply this kind of composition transformation to an element, let's say E, right? So we can apply the basic transformation, let's say F1 and F2 at each time. We apply F1, it will get E1, right? E1 at first, and then apply F2 from the inner transformation to the outer transformation. Then we can actually get the whole chain of thought reasoning trees and also get the final results by sequentially apply these rules. So in this way, later you will find this kind of design will allow us not only evaluate the final answer, but also evaluate the intermediate process and allow us to analyze the error large model may have during different case. And so after we know the basic component, the next step is we just design our experiment. As we just mentioned, we have three different scenario for the task generalization scenario. It try to investigate the extent to which channels of reasoning of LLMs transfer across different reasoning tasks, right? As we just mentioned, the task can be further decomposed into element and transformation, right? So here we consider them individually. We first consider the element generalization, then consider the transformation generalization. If you consider the real world scenario, because let's say if you consider like from a mathematical problem to healthcare problem, the context itself could be different, such as what I just such as from a mathematical reasoning problem to like a patient record, patient prediction task, and also the transformation here could be also different. Let's say for mathematical, it could be a reasoning task, but for the healthcare, it could be something related to the patient prediction task. So the context, also the relation are different. Because our underlying assumption is that the effectiveness of chain of thought reasoning is determined by the distributional discrepancy. Here in our work, we just design different kinds of scenario and to cover different distributional discrepancy. For example, we have in distribution scenario, conversation scenario, partially out of distributional scenario, and out of distributional scenario. Let's use transformation generalization as an example. For example, if we consider in distribution scenario, it could be pretty straightforward. The test distribution and the training distribution are from the same distribution, that is in distribution scenario. For the conversation scenario, the testing case would involve novel combinations that large model didn't see during the training process. For example, if we train large model on transformation, say F1, F1, F2, and F2, F1, and we try to test it on F2, F2. Here you can see that actually F2 as a basic transformation is already found during this training process, but this combination F2 F2 is novel, right? So by this way, introduce novel combination, we could introduce some kinds of distributional shift. A much larger distributional shift could refers to POD and OD scenario. For the POD scenario, probably the test case will involve some normal transformation that didn't send during the training process. For the OD scenario, even worse, the testing case just involve totally new transformation and a totally new combination that didn't see during the training process. So by manipulate the training data and the testing case, we actually can create this such kind of scenario and evaluate chain of thought reasoning of a large model. And actually, it's pretty like the theme for the element generalization in distribution are very straightforward. For the conversation scenario, we mainly consider the position as the position of the atom as these factors. For example, when we train large model, we can consider ABCD, but when we test it, when we test it, large model probably it will be DCBA. Because D never B in the training case it only appear in the fourth position, but in the testing case it will also show in the first, second, or third position, something like that. For the OD scenario, the testing case will involve totally new letters or all the totally new atoms, that is E, which is totally unseen during the training process, something like that. And for the second scenario, we try to investigate the robustness of chain of thought reasoning to reasoning chain of various lengths, right? Yeah, and almost following the same intuition, we also divided the length generalization into two parts. The first is test length generalization. Test length is actually refers to the length of an element, if you still remember. And for example, if we train large model in a length of in the test length of 4, how it perform in a length of 3 or 5. It refers to the practical scenario where you train large model on test in different lengths and you evaluate it. When you evaluate the problem, the test could be longer or shorter, right? And another scenario is reasoning step generalization. It try to investigate let's say the training. Let's use an example to illustrate. Let's say the training example use we train large model in a 2-step reasoning task, how it will perform in 1-step reasoning task or 3-step reasoning task, right? In this case, this distributional discrepancy can be measured by the length difference. That is the test length difference and the reasoning step length difference of this problem. For the format generalization, it actually try to investigate how sensitive chain of thought reasoning is to variation in prompt formulation and the structures. And here we actually we can use element as an example. For example, we design three different kinds of rules to perturb the element in the chain of thought. Let's say one method is used to insert one atom in the element. Another is delete is try to delete one atom in the within the element, or we can modify just one atom within the element. Here, actually, we apply a probability-based perturbation method. That is to say that each of the element is has a probability of let's say alpha to be perturbed by any of these three method. So here the distributional shift is pretty straightforward. That is a ratio of perturbation, right? So after we know how to design the experiment, the next step is that we can actually figure out the results. For example, for the task generalization, it includes the element generalization and the transformation generalization, right? And for this figure, we try to plot the performance of a chain of thought reasoning under different distributional shift scenario. Let's say from the red to the blue. Actually, the distributional from the blue to red, the distributional shift is become larger, right? And as you can you can see here, generally the blue score. Oh, it's important to mention that we actually use three different methods to evaluate our result. One is a blue score. It's kind of a very soft measurement. Another is edit distance. It's also a very soft measurement. And the last one is exact rate. That can be referred to the accuracy. It can be considered as a relatively hard metric to evaluate. As we can see here, when we increase the distributional discrepancy, the blue score decreased and the added distance increased, which can be taken as proof for our data distribution length. Also, for the element generalization, we try to investigate the results on various scenario and relations. We found that in the in-distribution scenario, typically a large model can perform very well. But for the CMP scenario and the out of distribution scenario, the effectiveness of chain of thought reasoning will decrease accordingly. And pretty like the same findings also found in the transformation generalization, like the table here. Collectively, we actually found that chain of thought reasoning cannot directly generalize to novel tasks involve ancient element or transformation. The effectiveness drops when the task distribution is shifted from the training data. When we actually go into the details, we try to evaluate different component of chain of thought reasoning. Just as we mentioned before, we can evaluate the reasoning trees as well as final answers, or the full chain to which allows us to have a more fine-grained results and insight. We actually figure out chain of thought reasoning show somehow inconsistent with the reasoning step and the answers. If you look at the first two rows, you will see that under this composition scenario, this chain of thought reasoning shows 100% for the reasoning trees, well, near to 0% accuracy for the answer prediction. So that's quite interesting. Also, if we still remember our example in the very beginning regarding the leap year and the normal year is pretty like the same. And this phenomena is opposite for some other case. Let's say from F1 to F2 to F2 F1. In this case, for the reasoning accuracy is 0, but the answer accuracy is 100. Um, we can explain explain it a little bit. That is, the large model try to replicate the pattern it sent during the training process and apply to the testing case. If you think about that, because F1 and F2 are cumulative itself, so if you change the order of this kind of two transformation, it won't affect the final results, but it will like affect the intermediate reasoning steps. So that's why this kind of scenario will happen. So based on this observation, we can find that chain of thought reasoning is not a very logical or faithful reasoning. Its accidental success is attributed to replicating patterns in the training data indicated by the inconsistency of reasoning and answer. And also, then because it already fails in the CMP scenario or out of distribution scenario, so we want to figure out in which case or in what scenario or when large model terms of reasoning will success. So to enable that, we try to add some data from the testing set distribution and see if we this a small proportion of data will have the results. Also, the results shows that even if we put on a small proportion of the testing data into the training data and use self supervised fine tuning, it will greatly increase the chain of thought reasoning's capacity. And this kind of increase is related to the also related to the distributional shift between the training data and the testing case. If you observe in this figure, for the CMP scenario, it will use the less proportion of data to gain a relatively high increase, right? Where in the out of distribution scenario, it will require much more data, right? And so in this way, we will say self-supervised fine-tuning, introduce self-supervised fine-tuning will definitely benefit the downstream task a little bit, a lot. So regarding the lens generalization, in the first experiment, we train large model on a test lens of 4 and evaluate it on 2, 3, 4, 5, 6. As you can see in this kind of figure, actually the performance of test lens generalization drops along with the distributional discrepancy. That is a difference between the test lens, right? So yeah, and also for the reasoning step generalization, we um, try to try to see the performance for reasoning step generalization across different training data components. Let's say we train large model on a two-step reasoning. We evaluate it on one-step reasoning or two-step reasoning. Here uh, and later we increase the component of one-step reasoning in the training data and decrease the two-step reasoning in the training data and see how it will perform during the test. Just as we expected, we can clearly see that the large model will perform better in the one-step reasoning, and the performance for two-step reasoning will decrease accordingly. So collaboratively, we will see that chain of reasoning cannot directly generalize to test case involve different test length or reasoning step, but by systematically vary the training data distribution, we see the forgot in the reasoning. With the original lens will adapt to that with the new lens. And then we try to figure out how the format generalization will affect the chance of reasoning capacity. And here, besides we consider the insertion, deletion, and modify, we also consider the combination of them. We can see here as we increase the noise level, the edit distance between the answer and the ground truth is also increased. So among these different perturbation approach, we will see the insertion method will affect the answer a lot. Also, we investigate, we apply noise on different area. In this experiment, we have the prompt area. We also can apply the noise to the transformation or the element area and see how it get affected. So if you can see here the prompt, if you apply the noise on prompt area, it will not affect the performance much. But if you apply to the K component, let's say the transformation component or the element component, it's actually the performance will drop a lot. So through this experiment, we can find out that transort reasoning is sensitive to format modifications. Apply a moderate level of format perturbation will greatly undermine its effectiveness. And finally, we also conduct some experiment under different temperature and the model size scenario. For the temperature, we try to replicate the element generalization under the scenario from the CMP POD to the OD scenario. We actually found that a change within a very certain range, within a certain range, if we change the temperature, the results won't get much affected. And also the similar results will be found in the different model size settings. Here we try to replicate the SFT scenario. You can see here, if we use model of different size, the results won't change that much, because at first it cannot generalize, right? So consider the temperature and the model size. We find that our finding holds across different model temperature and model size. So this kind of work also carries some discussion and implications. The first point I think is just guard against the over reliance and false confidence. Chain of thought is better. It cannot be considered as genuine reasoning, especially in the high stake domain such as finance, healthcare, education, law, this kind of thing. And also for this high risk domain, a sufficient audience from domain expertise in this principle. Also, we need to prioritize out of distribution tests because currently this kind of benchmark is relatively contaminated. So we cannot figure out if the benchmark already the large model already uses this benchmark to train or not. So in this way, we needed to probably figure out or create some new data set which satisfy the truly out of distribution scenario to evaluate the large model's capacity. The third point is we need to recognize the SFT as a patch, not a panacea. SFT can definitely is definitely helpful and can definitely quickly patch the model on a new specific data distribution, but we can never just rely on SFT to fix every OD feature, right? And so finally, we have some conclusions. Our results reveal that transfer reasoning is a broad mirage that vanish when it is pushed beyond the training distributions. This work offers a deeper understanding of why and when transfer reasoning fails. Emphasize the ongoing challenge of achieving genuine and generalizable reasoning. Finally, finally, let's provide some resources. We have some QR code for the paper, also for the code as well as Hugging Face. If you have any kind of problem, please feel free to contact me through email or you can reach it now. And I think probably that's it. Thank you so much for your time.
Thanks a lot, Chengshuai, for the nice talk. I think it's very informative. So people are recently talking a lot about COT, and you use this control experiment to view it from a data distribution shift perspective. Um, I do have some questions. I also see some audience online asking some questions about domain adaptation. So I think I also see many people talking about this. So I just wonder, can we view this work as a study on like why LMs fail at domain adaptation when relying solely on the COT? Do you think we can, or maybe we can add some more information on this, like how do you view it compared to domain adaptation?
Oh, I see, I see. I think it's a very interesting perspective. I think I think there's a lot of common interest between our work and the domain adaptation. I think the
Mhm,
more mainly similarity would be for the domain adaptation, they have some data for the target domain, and we train the model on the source domain, and want the model will also perform well on the target domain, right? It's pretty like the scenario we create in our paper. We try to use to try to create some distributional shift in the between the source domain and the target domain. We want to develop a method or a perspective that try to explain this kind of a phenomena,
mhm.
right? And currently, I also like notice that there are increasing effort working on the continual learning or similar domain generation or domain adaptation for large models. So I would say this could be a very promising and a very interesting direction to explore.
Exactly, very cool. And I also think it also depends on how you view the COT, right? I mean, for
Yes.
instance, in your paper, you view it as, I mean, if you treat COT as a mechanism for, let's say, emergent OD data synthesize. For instance, if you expect the COT to model some, or to model or invent some new logic, so basically they will fail. So basically, I mean, it appears as a marriage. But I mean, if you view the COT as a tool for searching, retrieving, or aggregating some information during the test time, so in that case, it also works very well, right? I mean,
Yes,
because it's
yes.
a very open topic. Yeah.
Yes, exactly. Although Charles out reasoning is not like a very general reasoning, just like human, it's not very
Mm,
faithful probably, but it can serve a very important tool when we understand the large model's decision. Somehow it can carry some insight as well as some step when large model makes some decision.
mhm.
Yeah, I think it's very important.
Yeah, exactly. Cool. I also have some questions about your experiment design. So,
Yeah.
firstly, I think it's very interesting. Like you basically simplify it and to make it be more controlled, so you can test out of different things. But maybe one thing I want to ask is about you called about the reasoning steps, right? So
Yes.
I think in your experiment, in your synthesis task, the reasoning step is very clear because you can control like how many steps it has. But I
Yeah.
think in some general natural language task, it's very hard to define how many steps are there. Or I mean, even for the same
Yes.
reasoning path, some people think it has two steps, some people think it has three steps. So I just wonder how it can generalize to other natural language tasks. I'm not
Mm.
sure how you think about that. Yeah.
That's a very practical issue, I would say.
Uh-huh.
As we just mentioned that we actually at first we try to map the real world NLP task to our settings first to make it more general and more clear. During this process, probably some key component is returned, such as this task length and format is returned. But uh, but due to its simplified framework and or environment, we want to make it more clear. So some other factors such as like the context, also some reasoning details will be omitted. So in this case, I
Mhm.
would say there's still a gap between between the real world case and our case. But
Yeah,
anyway, I think
exactly. Mhm.
it could be a will to explain and understand the real world case somehow.
Yeah, fully agree. And also, I have a question about the format. So maybe I missed some information you talk about. So the format is about the format of the prompt, right?
Yes, you are right.
Um, so could you please explain more? Like for instance, if it's a real prompt, what does A, B, C, D exactly mean here?
Oh, I see. Here we just give one example. Like let's say, first of all, the format generalization or the noise can be applied to three different area. The first is element area, another is transformation area, another is prompt area. So for simplicity, we just call them as a prompt scenario. It actually can be further developed it into three different area. For example, here we use the element, like when it apply to element area, you can see here, we actually can because we use this kind of a clean data to train large model, right? But in the real case, when user want to use a large model, they cannot directly figure out a way that can create a prompt exactly the same as us. So in this way, they create some noise prompt that could be some mistake. You can consider it as mistake when you write the prompt. And here's the three different approach. Let's say for the insert, you can definitely insert one or two noise into the element part. The same thing you can do is you insert some noise to the transformation part or the prompt part.
Mhm. That's your
So
point.
yeah.
Yeah, that's valid. Because previously I also thought about if we can study about the format of the reasoning process. Because I recently read some paper, I guess they are talking about, for instance, when a model do a chain of thought reasoning, if we look at the reasoning process, like what the model exactly outputs during the reasoning. So probably the format is more important. I mean, the structure is more important than the content itself. But I think these are two different things. So basically here the format is about the prompt, right?
Yes. That could be referred to another line of research which you use. You can design a certain prompt that instructs a large model to generate the intermediate reasoning
Mhm.
process following the for certain format, right? So
Exactly.
yeah, I also come across a few papers which indicate that probably when you prompt a large model and ask them to like output the answer in a maybe the program format or other related well-formed format like tabular data format, it will produce much more accurate result.
Yeah, exactly. Okay, and we have a question from the audience still about this slide. So, could Chengshuai you explain again what does A, B, C, D exactly mean? So, do they just mean the letters, or do they have any other meanings?
Uh, the ABCD here is actually refers to the element here, right? The I remember they actually as we just mentioned that we actually want to map this kind of different task in real world and the different element in real world into our data set first. Let's say our data set have some basic items, right? This can be considered as a token in the real world. And based on these tokens, we can formulate the element like Apple APVLE, also ABCD there is just like represent the text or passage in the real world.
Okay, so it's basically it represents tokens, right? So
Yes,
basically different. Yeah, I
yes,
see. I see. Cool.
yes.
And maybe also some further question is, do you think I shouldn't say the issue, but do you think all the observations you found in this paper, do you think it's also because of the training objective of the large language models? Because they only do next token prediction. So basically, they can only, I mean, copy the same pattern, right? They cannot
Yeah.
invent something. So what if we train using some other mechanisms. Like I guess there's something about process reward modeling, right? So
Yes,
if we
yes, yes.
can incorporate those kind of things, do you think it can somehow alleviate such
Yeah,
issue?
yeah. That's pretty like a very interesting and also very promising problem. I would like to share it a little bit. As you can see here in our theorem, it's actually composed of three different terms. Let's just ignore the last term. And for the first term, is actually refers to the model capacity, right? The model capacity I just mentioned is related to the architecture, also the parameter. But most importantly, there's another part that is just the training dynamics. That is the training strategy. You just mentioned that. For for that, I would say to overcome this out of distribution problem, because this is a kind of a very fundamental problem across all kinds of machine learning algorithms, also include large models, right? So I think we can definitely consider from the training dynamic problem. Maybe we can design some problem training dynamic that can go beyond the training data. Probably use process-based reward or other more promising
Yeah,
algorithm. Yeah.
exactly. I think it's not easy to solve now, right? But we can.
Yes.
There's also space to do that.
Yes.
Um, cool. I have one final question.
Yeah.
I don't see any other audience talking posting other questions. So because basically I think this paper is very interesting, but basically COT still works practically, right, in most cases. I
Yes.
just wonder, do you have any thoughts? Like for instance, if people want to use COT in real world, do you have any warning about that? Because I mean, uh, it's very hard to know whether a data is OD or not, right, in a real case.
Yes.
So, right, is there any practical guideline?
For the practical issue, I would say because I also come across another branch of paper maybe done by Anthropic. The basic idea is like a large model itself doesn't show your show the intermediate process as they thought. Probably they will give you a intermediate process or the reasoning process which look like what exactly they thought, but it's not true actually. So I would say for some problem, maybe some practical problem is not related to safety or highly risked domain, we can definitely use chain of thought as some hint or get some inspirations. But for the high stake domain, probably it's better to just use human in the loop or use some expert to check the answer and then apply it. It would be more beneficial in that way.
Exactly. Cool. I think let me check if anybody have any questions. Okay, I think it's all good, and we're also good on time. So, thank you, Chengshuai, again for sharing this interesting work. And for any audience, if you have any questions, please feel free to contact Chengshuai or us. Cool. Thanks again.
Thank
Thanks
you so
everybody for
much.
coming. Thank you.
Thank you so much.